Hello, my name is Andres Del Pino, and I'm currently a postdoc at the Space Telescope Science Institute. In this talk, I'm going to present you our latest results about the Sagittarius Dwarf Spheroidal Galaxy using Gaia data and machine learning techniques. This talk is based on a paper that just got accepted a few months ago, and I encourage anyone with doubts or willing to know more to go and check it out. But before running into details, I would like to present you the Sagittarius Galaxy itself. Sagittarius is one of the largest objects that can be observed, spanning several degrees in the sky, and it is also one of the closest to us, and yet, due to its location almost behind the Milky Way center, it wasn't discovered until 1994 by Rodrigo Ibata. What you see here is the figure from the original detection paper, in which you can see how the body of the galaxy stretched towards the Milky Way center, indicating that tidal forces could be playing an important role in shaping this galaxy. We now know that Sagittarius is a much more complex and larger system, and that its stars are being stripped from its main body as it falls into the Milky Way potential. These stars circle the entire sky several times, forming what is known as the Sagittarius stream, which is one of the best tracers of the Milky Way potential we have. The figure in the left shows an eye-tough projection of the stream where you can see some of its features like a prominent bifurcation. The figure in the right shows the stream as is seen from one side. A lot of effort has been made in the last decade trying to characterize the stream by means of N-body simulations. And here is an example based on a spherical pressure-supported model by Fodor et al. 2019 that does a great job at reproducing the general features of the stream. The modeling of the stream has led to a better understanding not only of the Sagittarius galaxy, but also about the Milky Way potential itself. However, spherical models struggle to reproduce some of the finest details in the stream, such as the observed spread in metallicity and the bifurcation in both the leading and the trailing arms. One proposed explanation for this is that Sagittarius was some sort of disky, gas-rich rotating galaxy, inclined some small angle with respect to its orbital plane around the Milky Way. The bifurcation could then be naturally explained by the stripping of stars with different angular momentum at different times. In the left figure, you can see the model proposed by Peñarrubia 2010 and how it reproduced the bifurcation. The same year, Walker et al. Presented their own model that shows the transformation from a disky Sagittarius progenitor into the spheroid we observe today after subsequent pericenter passages around the Milky Way. However, if this was the case, some residual rotation is expected to remain present in the Sagittarius galaxy, and none has been reported yet. However, all the studies up to date are based just on 2D position in the sky and line of sight velocities, which requires of assumptions about the 3D shape and the 3D velocities of the stars. Therefore, and just to summarize, studying Sagittarius can provide very useful information not only about this particular galaxy, but also about the Milky Way and the processes involved during the mergers of galaxies. In order to learn more, we need the full phase space of its stars, and by that I mean 3D positions and 3D velocities. The use of machine learning allows us to infer this full phase space without assuming explicit priors, and thus to observe the galaxy in 6 dimensions. But for that, we need a good data set, and it looks like Gaia is the best way to start. So we started by downloading the Gaia data in a cone region of 1 half-light radius around the center of Sagittarius that were compatible with the systemic proper motion of the galaxy. This resulted in 2.9 million of stars for which we have 2D positions and proper motions. However, this is just 4 dimensions and it has a lot of Milky Way stars polluting the sample. Because of the relatively large distance towards Sagittarius, all of its stars are too faint and don't have parallaxes precise enough as to derive stellar distances. Similarly, Gaia line of sight velocities are still limited to magnitudes brighter than G14, which is slightly brighter than the brightest stars in Sagittarius. In order to overcome these limitations, we made use of a list of nearly 9,000 RR-Lyrae stars for which we derived distances from their pulsation modes, and a list of nearly 3,000 giant stars with spectroscopic line of sight velocities. The basic idea is to use these external catalogs to derive the full phase space information in our Gaia main sample. In short, the process goes as follows. A model is trained to predict distances and line-of-sight velocities using the external catalogs, and then is used to predict such quantities in the main Gaia sample. Then we use a Gaussian model to select members in the 3D velocity space in order to not remove non-Gaussian spatial features. The whole process is repeated until no more stars are rejected, refining the model and the training vector in each iteration. And it turned out that the method works pretty well and it converged in just 4 iterations. The resulting final sample had approximately 120,000 stars, for which we estimated a maximum contamination of around 6% of Milky Way stars. Now that we have 6D, we can do all sorts of things. So the first thing we did was to create an interactive 3D view of the galaxy in order to study its general features. The figure is available and accessible to everyone in the web address that you can see in the bottom corner of the slide. You can rotate, zoom, and explore Sagittarius in detail. The color shade indicates the stellar density, and black cones shows the internal motion of the stars in relation to the center of mass. The systemic motion of the galaxy with respect to the Milky Way is shown by an orange arrow, and the blue arrow indicates the internal angular momentum of the galaxy. Lastly, a white dashed line shows the direction to the Milky Way center. There are a few conspicuous features that can already be seen in this figure, such as a more dense region in the center, a bar, and tidal tails that appears to emerge from the tips of the bar, conferring a characteristic S shape. It is also interesting to point out that the internal angular momentum is almost perpendicular to the systemic motion of the galaxy and to the vector pointing to the Milky Way center, meaning that Sagittarius is in a slightly inclined prograde orbit. If we project this view in 3 different planes, we can explore a bit more these details. Here, you see an exploded cube representing the projected view of Sagittarius in galactocentric coordinates. We found that the bar is approximately 2.5 kpc long and that it's inclined 43 degrees with respect to the plane of the sky. The galaxy is a triaxial system, which its longest axis aligned with the bar. However, tidal forces exerted by the Milky Way are disrupting and sharing Sagittarius, and the inclination of such axis changes depending on the considered radius. When analyzing the internal kinematics, we found that Sagittarius is expanding in its external regions, mostly along its longest principal axis. You can see such expansion projected over the longest, intermediate, and shorter principal axis of Sagittarius in the left columns of these plots, where a red line shows a Bochcar average of the stellar velocities and positive values indicate expansion. The right column shows the stellar rotation measured about the same axis, where the influence of the Milky Way tidal forces can be observed as precession and nutation. Interestingly, we found that there is an inner region that is not expanding or contracting and that it's rotating at around 4 km per second. In order to explain to which kind of progenitor these morphological and kinematical features correspond to, we compared our machine learning predictions with 3 different M-body models, 2 of them based on a spherical pressure-supported progenitor for Sagittarius, and another one based on a flattened rotating disk that is inclined with respect to the orbital plane. We found out that the best overall model was the rotating one, which was the only one able to reproduce the bar and the orientation of the internal angular momentum. In these plots, you can see the rotating M-body model after letting it evolve until the current state of Sagittarius, and in the right, you have the Gaia plus machine learning predictions. So, I hope to have convinced you that Sagittarius is a very interesting object to study, and that machine learning techniques are very useful with Gaia data. The findings from this work indicate that before being accreted, Sagittarius was a flattened system to some extent, and that it had some rotation, meaning that it probably looked more like this picture of IC-59 rather than the Dwarf Spheroidal Galaxy we observe today. And with that, I will leave it here with the main conclusions of this work. Thank you very much.